All right, so this is our last lecture of the semester, and this is a chapter that it involves some, no, it gets a little bit complicated right off the bat because we talk about moving something across a membrane, and we talk about basically whether or not something is favorable. So membrane transport is kind of what we're going to refer to this as. So when we transport across a membrane, we're talking about diffusing a substance between two sides of the membrane and how that thermodynamically resembles a chemical equilibrium. Okay, so this does take you back to Gen Chem 2 a little bit because thermodynamics and equilibrium, we're talking about like an equilibrium, we're talking about a ratio. Um, and ultimately, when we do that, we can start talking about things like, where's my tablet? That's not what oh, there we go. That's why I couldn't see it. We're talking about delta G, and we're talking about whether or not, is it a positive or a negative delta G? Is it a favorable or an unfavorable move? So when we talk about a chemical equilibrium, we can think about it as um, so we can kind of think about this as being analogous to reactant and a product. Uh, but rather than, a bond being broken or something like that, or bonds being formed, instead we're talking about a substance that starts or has a source where it's coming from, and then it goes to destination, kind of its final place. So the difference in the concentration of a substance on two sides of the membrane generates a chemical potential difference. Okay, so we've got a chemical potential difference. Now that chemical potential difference is best described as delta G is equal to R, which is our gas constant, times T, which is our temperature, times the natural log of our product divided by our reactant concentration. So we can look at this as effectively we're looking at the delta G, the free energy of something being on two sides of a membrane, and we can relate that to equilibrium. What are the two concentrations of these substances? And how does that relate to our delta G, our free energy of a reaction? Now, the movement of ions across the membrane also results in a charge difference. Okay, so here's, this part right here, movement of ions. Okay, so what's an ion? Well, Na plus is an ion, K plus is an ion. Sodium and potassium are ions. What is not an ion? Glucose. Okay, so the movement of ions across the membrane also results in a charge difference, generating an electrical potential difference. So effectively, what this is saying is that when you move something like any substance, on two sides of a membrane, well, that's going to generate a chemical potential difference. If that substance happens to be an ion, well, then that's going to develop an electrical potential difference. The electrical potential difference is best described as Z sub alpha or Z sub A times Faraday's constant times delta psi. Z sub A is the charge of that ion. So sodium, for instance, would be +1. Faraday's constant, or F, is 96,485 joules per volt mole, or it's 96.485 kilojoules per volt mole. Delta psi is our membrane potential. The units for this are in volts. Now, effectively what this means is when we talk about different concentration differences of substances on two different sides of a membrane, we have to account for their chemical potential and their electrical potential. And we combine all of that into an electrical or electrochemical potential. So delta G is equal to RT times the natural log of our product or our concentration in the destination divided our concentration in the source plus Z sub A times F times delta psi. Now, membrane potential. Well, we use that to calculate this sort of, or to answer a question related to this and do these sorts of calculations. We say by default delta psi, so that right there is measured as the potential inside the cell minus the potential outside the cell. So that is like there's a convention, there's a standard. This is the default. Delta psi is inside versus out. So destination minus source. So this right here is a little bit of foreshadowing. A negative number indicates the inside of a cell is more negative than the outside. If an ion moves from the outside to the inside, then the membrane potential is fine. What that means is that if you see a question where you say that delta psi for this is negative 0.5 volts, that is saying to move this substance from the outside to the inside, it is a change of negative 0.5 volts. That's your convention. The delta psi for that is negative 0.5. Now, if an ion, however, moves from the inside to the outside, then the sign of the membrane potential must change. So we'll see this in just a second, but I think that it's always challenging when you see a question where you're like, oh, I have this value. Do I need to change? Do I need to make the negative value positive? Do I need to make the positive value negative? And the answer is yes, in these circumstances. Okay. Almost always the cytosol is considered the inside. Additionally, if more than one ion is transported, calculate the free energy change from one ion, then multiply for additional ions. So with this question right here, we have this question of, is it favorable from a charge standpoint to transport chloride ions into a cell when delta psi is negative 60 millivolts? Okay, so let's evaluate this. This question, we've identified our ion, chloride. All of this information down here at the bottom where I put my star is kind of irrelevant to this. It's not asking us about this. Instead, what it is asking is basically when we bring all of our values here, do we get a delta G that is negative or positive? And so let's go ahead and sort this out. What we have is a Z sub A that is negative because chloride is a negative ion. We have Faraday's constant. For all intents and purposes, we could just put that as 1 because we don't really care about quantifying this. We just want to know, is it positive or negative? And since Faraday's constant is a positive value, we could put any positive value in there. So I'm just going to put 1. It's a filler, basically. Then the question is, we have a delta psi value. That delta psi value is negative 60 millivolts. Let's call it negative 6 just for simplicity's sake. Or heck, we could just make it's a negative value. The question is, when we go to put it in here, delta psi for this specific question, Do we need to change that symbol from negative to positive? Well, before we answer that question, let's look at what is taking place. Is it favorable from a charge standpoint to transport a chloride ion into a cell? Okay, so we're going from the outside in. And let's look at this first point. If an ion moves from the outside in, then the membrane potential is fine. Okay, we are going into a cell, which is the same as from the outside in. And so I'm going to give this a negative value. So we have effectively negative times 1 times negative. Well, a negative times a negative is going to give us a positive value. So we're going to get a delta G, which is positive, which means the answer to this question, is this favorable? No. If we were going in the opposite direction, if we were going from the inside of the cell out, then it would be favorable. So now if we think about this from the opposite perspective, well, what about transporting it out? Okay, so now we have to reflect on this. If an ion moves from the inside to the outside, then the sign of the potential must change. The charge of the ion does not. So effectively what we're doing is we're revisiting this part of our equation. Z sub A, so we've got negative times, and I'm just going to drop that placeholder for Faraday's constant. And then my delta psi is positive. So that means I've got negative times positive, which is going to give me a negative value. So that means that the delta G is negative. So this is favorable. Now, here is a very similar question, but we're adding more to it. Now, part of this calculation will simplify some of that natural log stuff that we've got in this calculation. But essentially this question reads, transporting sodium ions in or out of a cell with the delta psi is negative 60 millivolts. The cytosolic Na plus is 12 millimolar. The extracellular Na plus is 145 millimolar. Okay, so this gives us a destination and a source. Now, what is the change in free energy associated with transporting sodium into the cell at the body temperature of 37 degrees Celsius? In order to do this calculation, we can break this into two different parts, and we can look at this as the chemical potential. So we'll take the R value of 0.008315 kilojoules per mole Kelvin times 310, which is our temperature. So this effectively is R. This is T, and then natural log of our destination concentration divided by our source concentration. Okay, so our destination is, we're sending sodium into, so our destination is the cytosol. So this is lowercase d for destination, and 145 is our source because it's coming from outside of the cell. This is ultimately going to give us a chemical potential of negative 6.42 kilojoules per mole. So from a chemical perspective, this is favorable. Now, the follow-up to this, however, is we need to get the second half of the equation taken care of and accounted for. So the second half of the equation, and this right here is just a sort of simplified rundown of the same calculation, rounding some numbers. Rather than 12 and 145, you make them a little bit nicer and you say, well, 15 divided by 10. And so that effectively means what is the, rather than the natural log, what's the log of 1 over 10 or 0.1? Okay, so now the second part of the equation is right here, the electrical potential. Okay, so our Z sub alpha is our charge of our ion. This is a sodium ion. That's a charge of +1. We have Faraday's constant, which is 96.485 kilojoules per volt mole.